So yeah, we'd like to welcome Guangbo Xu for his second talk about the Hamiltonian Arnold conjecture obviously.
Thanks. Thanks again for accommodating my needs. And so I decided to change the number of lectures from 3 to 4. But each time I will try to keep it within 75 minutes. So today I'm going to basically review the global chart construction by arXiv mathematics, and the next time I will explain how to generalize their construction to Floer moduli spaces or Floer flow categories. Then in the fourth talk, I will just wrap things up and to give you the to basically finish the proof. Okay, so here is the reference of my lecture today. So it is on arXiv, appeared last year. Okay, so last time we used notion of derived orbifold charts, which are basically orbifolds on top of which there is an orbifold vector bundle. So this time we're going to specialize a little bit. We're going to use a more specific kinds of charts, which we will call Carnacci charts or K charts. So basically, we will have these two kinds of charts in this story. So let me first give you the definition of what do I mean by a global Carnacci chart on topological space. So that X be some topological space. A global Carnacci chart on X is a tuple, or we call it a K chart. Is K E B E as in the psi, where G is a compact Lie group. V is a topological manifold. G manifold with at most finite stabilizers. E is an equivalent G bundle. The G equivalent section. And the psi is a homomorphism between the orbit space of orbits of the zero locus to the topological space X. It is called a smooth chart if VE are smooth and the G actions
so S doesn't have to be.
S doesn't have to be. S can be just continuous. Yeah, as before, like S just tell you, where the zero locus is, and you just work locally there. It doesn't have to be, but you always perturb it. So this is the definition of K chart, Carnacci chart. And we can see that if it is smooth, then you can just quotient everything by the symmetry group G, you get a orbifold because we assume that it has only finite stabilizers. You also get an orbifold vector bundle by quotienting E mod G. And then from a smooth Kranich chart, you get actually the derived orbifold chart. And this the key point of today's this construction is
Another question. So, are there not in the literature results about this, about when you do Morita equivalence, that you can write an orbifold as a global quotient?
Yes.
So there must be something that's related.
Right. If you have, effective orbifolds, yes.
Yeah.
But the construction is the other way because I mean smoothness is the issue. I don't know if in topological category that theorem is also true or not.
Okay, something to be understood. Yeah.
So today's goal is to.
But in principle, I mean, this stuff comes from modulized spaces and homomorphic curves, so you can make the ambient spaces smooth, I would say, if you work harder.
Yeah, of course. Yes. So today's goal is to review Abzai MacLean's construction of a smooth A-part. This modulus space of Gina 0. Moduli space of Gina 0 stable maps with no mark points for some degree and some choice of almost complex structure. So let's fix the compact symplectic manifold, a compatible almost complex structure J, and the homology class. And then you can have this moduli space. So for this construction, we need to choose an auxiliary symplectic form. Space. Capital omega, which is tamed by J. So let's denote this pairing. Between this integral form omega and the class A. So this this moduli space is quite singular, and the idea basically is to put this guy inside something bigger, something containing more geometric data, and you use the extra geometric data to perturb the Cauchy-Riemann equation, so that in this thicker geometric moduli space, everything becomes regular, at least near the original moduli space. You're going to include more geometric data or geometric objects. Okay, so let's first look at an actual point in this moduli space, which can be represented by a J-homomorphic curve. So suppose represents the point in this moduli space. So let's just call it MR. So then, because the capital omega is tamed by J, and you actually, if you pull back this omega by U to the domain, this is a positive two form, everywhere positive. And also the integration of these two forms is integer. So then you can realize this form as the, up to 2 pi I, the curvature of some line bundle. So then there is unique holomorphic line bundle LU over this domain sigma, which could be a nodal curve whose curvature is minus 2 pi I times this form, and the degree of this line bundle is d. So this is where we use the GINA zero condition, because on a GINA zero curve, you have a unique holomorphic structure of any line bundle. But in higher genus case, this holomorphic structure is not unique. You have a Jacobian variety parameterizing the possible holomorphic structures. So this is something you can obtain by choosing this capital omega. And also this is a positive line bundle, so you can basically describe this holomorphic structure by using a bunch of sections. So let me introduce this visual notion. It's called a frame curve. Yes.
Sorry, I have a question.
Yes.
If it's nodal,
Yeah.
the domain is not connected.
It's connected.
Oh,
Yeah.
you're considering it as just like a single.
Yeah. Right. So it's a continuous line bundle over this nodal curve, which is holomorphic on the smooth part, and also the permission structure is continuous at nodal points. So that, yeah, it defines an actual continuous. Yeah. And even in that case, you can show that there exists unique one. So this is true for any J holomorphic curve, and this is also the positivity condition is also true for anything that is almost nearly holomorphic. So let's say a framed curve plus A is a tuple triple U sigma and F, where sigma is the nodal genus zero curve. It's smooth such that U star omega is everywhere positive. And F is a D+1 holomorphic sections of the associated line bundle is a basis H upper zero of this associated line bundle. So we actually identify F with lambda F or any non-zero scalar. If two bases differ by a common factor, then they are regarded as equivalent. So this is our first set of actual geometric data, and you can use the frames to produce possible perturbations to the equation. So if you have such a frame curve, which is a smooth map and together with a bunch of holomorphic sections, then these holomorphic sections can produce a map into a projective space. degree of So actually every framed curve will induce a map into the d-dimensional projective space of degree d. And also we can require that, by imposing an open condition that every, the usual stability condition, if it is a degree 0 map, if it is degree 0 map, then it is constant, things like that. And then we're looking at a particular locus of this associated moduli space. So this is the moduli space of maps into CBD of this degree D, and which we consider those the subset which arises from this kind of construction. We denote this open set by FD, which is the set of maps to CPD of D. This images are not in a hyperplane. Or equivalently, it just means that it is induced from a basis of H0 of some line orbital. And the important property of this open set is that this guy might be singular, for example, when there's multiple covers. But this one is smooth. This one is smooth manifold. So you can actually prove this. And also now we can actually transform the symmetry of the original holomorphic curves into the symmetry inside this object. So actually on CPD, there is a linear action by the projectivized unitary group. P of U equals 1 acts on CPD in the obvious way, which induces an action FD. And there is another object which is actually the universal curve of this FD. Universal curve. It is also U equals 1. Manifold. The universal curve means that you just it is a map from CD to FD, where each fiber is just the curve itself.
Wait, who's CD?
CD is the universal curve. So this guy is a part of a moduli space into CPD. So the universal curve is just a pairs of Z and X, where X is in here and Z is in a point on the domain.
It's like the fiber bundle over FD, whose fiber is just the curve.
Or you can think this as this is just the corresponding M01. You have an extra mark point. This one has no mark point, and CD is the corresponding moduli space is one mark point.
Okay, so that's how you define the PU.
Yeah, POD plus one action is just the linear action of the projected space, and you can just transform all the curves by this linear action on the ambient CP. But if your map is coming from this basis of this H0, then the PUD plus one action is just a linear action on this vector. Or it's just like a changing basis. Any more questions? Okay, so now let me describe the global chart as a set. So let's choose positive integer k. Actually, let's see. So first, the thickened moduli space. K is the moduli of quadruples. Where u sigma f is a frame curve in class A. Eta is a section, is a holomorphic section of something. Satisfying something. I'll pause here.
Yeah, you
What is
can,
K?
Okay.
What is K?
K is we choose a large integer.
Oh, choose large K, okay.
So let me explain this very involved definition. So we just have you can consider all the frame curves, like for example, nearly holomorphic, near your actual J holomorphic curves, and together with another data, eta, which is some vector in some vector space. And this guy is this vector space is the tensor product of two complex vector spaces. And the first one is H0 of some complex Hermitian vector bundle over the domain curve sigma. And this is also the space of holomorphic sections of some line bundle over the curve sigma. So the second factor is easy. So you have a framings and you induce a map alpha f from sigma to CPD, and you pull back this canonical, OK over CPD. And because K is positive and your map is also a holomorphic map, then this line bundle is a positive line bundle. So you have a, if K is large, you have a lot of holomorphic sections here. And this vector bundle is that you have this bundle of conjugate linear homomorphisms from the pullback of the tangent bundle of CPD to the pullback of the tangent bundle of the manifold, and tensor with this pullback of the line bundle. So the purpose here is also to make everything very positive, so that you don't have H1 or you don't have H1. And then this actual piece of data together with your framing can be used to define some perturbation terms here.
So let me start. So I'm looking at the holomorphic curves in the original unperturbed setting, and I want to associate to this some line bundle.
Yes.
And ideally some holomorphic line bundle.
Yes.
And then if that line bundle would be very positive, I would have a lot of sections.
Yes.
And then, so what I'm describing now maybe is the zero Fourier coefficient of what you do. So I have a lot of sections, and then that means I get a vector space, and I could use that actually as a parameter for perturbation.
Right.
Yes. Direction we go. Yeah?
Yes. You're right. Yeah. You just have a lot of extra sections if K is large.
So I think modulo whatever the letters are there, it is really you start with your holomorphic curve and neighboring constructions. You construct some holomorphic bundle which is ample or something very positive. You have a lot of sections on this, and you make it sort of sufficiently natural, and then you can use that vector space as parameters for the perturbation.
Right.
And then when you want to do it concretely, you have to write a lot of letters.
This like the place where this eta lives is just like it's where it has to live for this no bar equation to even make any sense, right? Like if I wanted to pull something back via this embedding into this projective space such that it was equal to the del bar J thing.
It's a very concrete geometric way to produce to choose a large finite dimensional space of perturbations into perturbed equation to make it transverse.
And it's also some nice behavior with respect to bubbling off.
Yes.
And so on, which of course can also
okay, sure. It also has to be
of naturality of the it has to be rather low on something that has this property. So I think that. But so the idea of using this initial line bundle, I think that goes back to either Siebert
So okay.
And that's a long time ago.
Okay. So So let me just explain this term here. So eta is, you have two back factors of this line bundle, and one is complex linear, one is conjugate linear permission pairing between these two parts. And then after you contract these two factors, you get something from here, which is conjugate linear maps from the tangent from this tangent space to this tangent space. And then if you compose with this linear map, which is complex linear, then you get something which is type 01. So this is a set which is described by the moduli space of this quadruples, and you module some natural equivalence relation. And there is also the action by this PU D+1. This is just action induced from action on the projective space. And now we need to describe the obstruction bundle. So the obstruction bundle is the direct sum of two parts. So the first one is just where eta belongs to.
So E sub K and then there's no K on the other.
Okay, I can write K here. But there are, yeah, let's do that. K is just right. So where the fibers of OK are just this vector space. Is the bundle fiber positive definitely. The Q factor is just this, as a set, it's a space of D+1 times D+1 positive definite Hermitian matrices modulo the scalar multiplication by positive real number. It's not a vector space, but near the identity matrix, you can view it as something like a vector space. So like using the exponential map of Hermitian matrices. And the section S, the Greenwich section, roughly, is just by evaluating the vector eta, and also you just compute the Hermitian matrix of your framing using the Hermitian metric on the line bundle and also the pullback symplectic form.
What happened to you?
U is your.
That was the origin. That was that's the map from Riemann surface.
Yeah, the Riemann surface to the symplectic manifold.
So the section. So what do you mean by section S? Is that the perturbation?
Yeah, we want to define a manifold V, a bundle E, and a section. so that modular symmetry is identified with the moduli space, original moduli space.
Yeah, I just tried to understand. So originally we have in the ambience. Okay, so we have this particular modular space, and then you define. So now I have to understand what happens precisely. So then you take a neighborhood in something.
Oh, okay. Let me.
I mean, or if I go further back in a more primitive, I would have a Cauchy-Riemann, I would have an ambient space, I would have a Cauchy-Riemann operator, plus have additional structures and so on. And so therefore, I wonder what you're talking about.
Can I try to say so that maybe I understand it? So this thing, so you want the section such that the zero set is the original home of your current space, right? And that happens exactly when. So if when eta is zero, so that the thing satisfies the Del-Bar equation. Yeah. And when the F's all are zero, because
right. Okay. So I should say the zero locus or the zero section of this obstruction bundle.
Space. Okay, so I forgot actually. Okay, good.
Yeah. So the zero location should be where eta equal to zero and where this matrix is like identity matrix. So basically, this section you wanna fill eta, so there's no obstruction to the equation. I mean, no perturbation to the equation, and also, but the framing you have like a lot of choices for framing, and this one is to normalize the choice of framing. Yes.
Sorry. So then are you also doing something like the PU and like your quote in the moduli space here, you're quotienting by the PU equals function, and then that's why what the identity thing is a unique element of your moduli space on that.
Yeah. So the vanishing of this one tells you that it is also normal basis.
Yeah, and there's one orthonormal basis.
So so that basically tells us how to prove the next lemma. And actually, this also not just identify these two sets, but also identify the isotropy subgroups. So you can, if you just it's fairly elementary to verify that if there is a curve which has automorphism, then that automorphism is equivalent to a corresponding point in orbit and an element in or an automorphism. Element in the isotropic group inside this largely group. Okay, so this gives us a description of the global chart without showing that this BK is actually a topological manifold. So next step is to show that if we choose this K large enough, then that can make this set BK a topological manifold. I mean, it has a natural topology. You can define the say Gromov type topology on this modular space BK. Or large enough K.
So I think in principle, with this kind of problem, so we start with the original moduli space. So you want to say thicken it in the ambient space, and you want to have construction of a parameter set which would decompose, would decompose if the underlying curve decomposes, and then in principle, if the parameter space is big enough, one would get such a structure.
Right.
So I think that's an implementation of such an idea, and there might be other ones as well.
Right. That's perfectly possible. Okay, so for large enough K, VK is a manifold linear 0 to plus. Well, maybe I don't explain the, I write down details of the proof, but the basic idea is that those line bundles are very positive. There's plenty of sections, and if you like K goes to infinity, then that basically can approximate to any, say bound functions on the surface. So that if K is sufficiently large, there is a large vector space here, and that can if you have a genuine J-holomorphic curve, then adding this part of perturbation, you can always use the use this part to kill all the cokernels. And you can prove that for every point there is some large enough K so that you can regularize that point. Then by compactness you can find a common.
So for showing that the structured model is a topological vector model, is kind of the same. You need like local truth.
Yeah, you need some kind of gluing, but basically there's the positivity tells that there's no H1, and if you really want to show that, you can just if you have a nodal curve, you can glue those holomorphic sections near the node and produce nearby holomorphic sections of the line bundle. I mean, you don't put any structure, you just show that this is a manifold. You just need to construct one near every point, one part near every point. Okay. Well, so that explains that the curves are how to say, this equation is surjective. If you linearize this equation at every point, it is surjective. Now there's another part which is gluing. You have to also show that if the curve, if you have a singular domain and the resolving these nodes also produce you parameters of the space, then you have to do the gluing part. And there's a key point here is that so there is a natural forgetful map from VK to FD by forgetting by forgetting the map into the symplectic manifold, and you only record the map into the projective space. And this guy is inside. And indeed, this guy plays the role as some kind of the Limon space. Remember when you do gluing holomorphic curves, if there's no enough marked points and the domains are unstable, the usual way to do the gluing is to add artificially more marked points to stabilize the domain. And then you can by choosing those actual marked points, then the domains can be canonically parameterized near a singular one, and then you can do the gluing construction. And here you just have a different way to sort of parameterize the domain, although those curves in those domains are unstable. So one particular way to explain that is I just choose arbitrary, generic hyperplanes in CPD and cut those curves, and this can produce you a locally a good parameterization as if you have chosen extra mark points. So this is the construction of the global coordinate chart as a topological object, topological coordinate chart. More questions? So the next thing is to put a smooth structure on those global charts. Or this one global chart. So the approach of upside McLean-Smith is to use some more artificial and concrete smoothing construction without referring to a lot, or using limited information from this moduli space. So we don't try to understand how curves degenerate and try to put the right coordinates on the gluing parameter, space of gluing parameters. Instead, we just use or refer to some general fact in smoothing theory to cook up a abstract smooth structure. Okay. So let me just tell you a little bit background. So we need to review something about the microbundles and the topological methods.
I mean, when you look at this moduli space, so there might be a lot of things who are where you have certain activity already without even perturbing, and then you would get sort of a natural smooth structure there, which might actually be important for maybe not precisely here, but later if you have evaluation maps and so on, they only are smooth or good enough if the smooth structure at certain places is sort of the right one. And so does that take that into consideration?
No.
So that means now if in future somebody writes, it's easily seen that this generalizes to this situation, it might actually not true. Okay, so
I would say it's not exactly. There's no way to see. There's no way to see that you get a canonical smooth structure, but I think it's possible that you get a canonical smooth structure up to some weaker, it's called isotopic class of smooth structures, something like that.
But that might already be quite different. I mean, when you look at smooth structures on the real line, you have x to the cubed and the identity, and so on. So it has all kinds of different properties of zeros. So I mean, in some sense, for further work, when you have marked points and so on, so then an evaluation maps and you pull back differential forms and do this and that, and that doesn't work.
You don't have. You surely this one doesn't give you a canonic.
But I'm pretty sure in the future you will find a paper that's easy.
Okay. So I'll quickly tell you how to do smoothing of a topological manifold. So let me introduce this concept of, or review this concept of microbundles. So a microbundle on a space X is this diagram. Like that. Here, this bundle E, it looks like. So you can view this object as some kind of vector bundle, but instead we just require that near the zero locus, it looks like a product.
So do I read the U versus sub?
Ux is
U sub X.
some neighborhood. And you don't require the structure group is a linear group.
Is this the same as being, what's it called, a topological submersion?
I have to check that. I don't know. But let me give you two examples. The first one example is,
Well, that's not a real definition. I mean,
yeah, it's not a real definition, but yeah. But let me give you examples to say what's there. The first one is that if you have an actual vector bundle, then you have a micro bundle. And a vector bundle with a micro bundle. And if X is a logical manifold, it's tangent microbundle. Its tangent microbundle is this one. You just embed X in as a diagonal into X cross X, and then the projection you project onto the first coordinate. And this one is the microbundle is exactly restating that X is the topological manifold. Well, I will also skip the definition of microbundle maps and the microbundle equivalence. So basic fact is that if X admits a smooth structure, then let's call this T mu X. T mu X is equivalent to a vector bundle. Because you can, one concrete way to show that to construct such an equivalence is to impose to choose a Riemannian metric and to use exponential map. So we can think that
It's kind of local near the section.
yes, equivalence just means so two microbundles are equivalent if there are forward and backward maps such that two-way compositions are identical near the zero locus, near the zero section. Yeah. So this gives you a necessary condition for a topological manifold that meets a smooth structure, and this is almost a sufficient condition. So, but now let me incorporate the group action into this picture. So first, non-equivariant case. So, X be a topological manifold, a stable smoothing is a smooth structure on X from star A, some K. And if X is a G manifold, it's stable G smoothing is smooth. Is a smooth structure of smooth G manifold cross R or some representation. And the tangent microbundle admitting a vector bundle leaf or is equivalent to a vector bundle is actually a sufficient condition for X admitting a stable smoothing. I mean, there are some weird phenomena in dimension 4 which actually says that we don't have those good things in dimension 4.
So when one defines this modularized space, so then they show it as a topological structure.
Yeah, topological maps.
So it is a choice topology. So basically, to avoid going into the way how they're doing it.
Yeah, avoid the hard things.
Okay. Okay.
Yes. So okay. So let me state the theorem by Laplace, which is so if the tangent microbundle of a G manifold X, where G is a compact group, equivalent is G equivalently equivalent to a G vector bundle. Then X admits a stable G smoothing. So this will produce once you can, for any topological manifold with an action by G, if you can find this equivalence between the tangent macrobundle to some vector bundle, then you can cook up a smooth structure up to multiplying by an additional factor, which is a representation of the group. But this is actually perfectly fine because this just corresponding in the moduli problem that you add more obstructions. You can just treat this actual factor. If X is your thickened moduli space, if you multiply this space by an actual vector space, you can also add this to the obstruction bundle, and that just means that you can artificially create more obstructions. But that doesn't change the problem you're working with.
But we mean you have more parameters.
You have more parameters, yes. But yeah, let me maybe. But then the section S you can just fill. On the domain you have actual R. On the obstruction space you also have actual R. You just cancel them. Yeah. So now
Ask a question. I'm not, so why do we need this exactly? Can you just back up and just remind me why we need this?
Because it's extremely hard to construct smooth structures on any moduli spaces.
Okay, even on this, because weren't you saying that it's a manifold near S?
Topological manifold.
Okay, that's what I was confused by. I thought you were saying that you could just achieve regularity there.
Topological.
Not, in a way that
they have the different stratas where it's smooth, and you glue them together.
Oh, okay.
And then you choose, you want to mumble something and say the whole thing is a topological manifold, or you actually do the analysis and show that the data is actually smooth associated. Yeah. They didn't want to do that part.
I see.
So how come nobody tried this like a long time ago?
Well, in protocol, that's probably not. After picking a glue profile.
I meant this very specific.
Okay.
Like the smoothing.
Yeah, well, that's new. Yeah, that's new.
Yeah.
To many people, I think. Okay, so now how let's try to go back to this concrete situation. How to smooth this second moduli space? So let's use this, make use of this map. Go back to the second moduli. So we have this map. So first, this guy is smooth. This guy is smooth. This is the part of the moduli space of maps into projective space. That is an algebraic object. There is a canonical smooth structure because you can describe this as a Zariski open set in some variety.
Oh, what did you say? So FD has a smooth structure.
Yeah, this is inside the heap, which is an algebraic object. This has a smooth structure. And canonical says a smooth structure. And also, there is also the universal curve, which is also has a canonical smooth structure. This is also an algebraic object. And this data can one usage of this data is that this data tells you or fixes the domain of the map into the symplectic manifold. So that means if you look at the fiber of this map, if you fix one point, P. If you look at one fiber of this projection, this can be viewed as a set of maps from a fixed domain into the symplectic manifold. So that means the fiber has a canonical smooth structure from the nonlinear problem. Yeah, so basically we have a sort of a submersion. Actually, this is called a topological submersion also. So that the base of the submersion has a smooth structure and the fibers has canonical smooth structures. So you actually have some candidate vector bundle. That is the direct sum of the tangent bundle of the base and direct sum of the vertical tangent bundles. So then the rest, so let me say, there's a little bit more analysis to be done. You have to show that the fiberized smooth structure varies sort of continuously. So that's.
Did you look at this last thing?
Yeah.
How long is it?
Not too long.
Not too long.
Yeah, it's very explicit construction. Yeah. Let's take the potential. The fiberized smooth structure. Varies in a so-called C1 local way. That implies vertical tangent bundle. Yeah, there is a little bit more. You have to look at the proof of the gluing theorem actually to derive this thing. So then one has a candidate tangent bundle. And the rest is to show that there is some microbundle map from this guy to the microbundle of the total thickened moduli space. And this is some elementary construction. Basically, you just work it locally and you extend from every chart to a larger piece of the domain, and then you extend bit by bit. Then you can cook up this microbundle map from this vector bundle to this tangent microbundle, which is an equivalence. And then you appeal to Lascelles theorem, and that shows you that if you
The original, so who came up with this microbundle stuff?
Milner, yeah, that was like in the 50s.
No, so that when it was interested in this one.
So then,
But if the microbundle is already sort of smooth in some way, then
Yeah.
That would pin down the precise smooth structure.
so the microbundle is just this guy. So if both are smooth manifolds, then everything, of course, is
Then I could so like a linearize something.
yeah.
I wonder, because here are certain things you construct, yeah, on the strata are actually smooth. I mean, the fiber is smooth. So I wonder then if the microbundle construction is a little bit refined by saying on certain parts we already then have.
Yeah, that's actually the in our paper of the Arnold conjecture, we actually say we have to prove a relative version of this one. So suppose on the open side you already have a smooth, everything smooth, then you can just extend.
So a priori, if you have this tangent, if it's smooth, then there's some, and then you have some equivalence to the tangent.
Right. So for example, the microbundle. Right. So you can think this tangent microbundle is like something at every point X you describe nearby points, and you can choose, say, a remaining metric, use exponential map to map a neighborhood of the zero locus of the tangent bundle to anything near a particular point, and to cook up this a microbundle map.
I think my statement was poorly phrased. It's so there's some natural equivalence with the tangent bundle, but you could have other. Is it true that for any equivalence with some abstract vector bundle, you recover your original smooth structure from the smoothing theorem? Or
no, I mean, if you like on the one topological manifold, you have different smooth structures, right? So
yeah, I see. Yeah, fair enough.
So yeah, so then you apply Lascelles theorem to show that there exists a representation of P(U)(1) and a structure of smooth P(U)(1) on manifold having VK cross power. Then redefine
So we define, so the arrow just means replace sub A by
replace. Replace. Let me take it right more. Let me just write this as like a precise thing. Okay. We define a new chart. A new chart, which we call the stabilization of the original chart. which is VK plus R, EK direct sum R, S A direct sum is identity R, and psi theta, where, sorry, there is G. This one. This part as the structure. And so, and once the domain is smooth, it's, the bundle, if you have just a C0 vector bundle, you can always equate a smooth structure on the bundle. So you can just arbitrarily do that. And any two choices will be isomorphic actually. So basically you thicken this modular space again, but also you thicken this structure bundle by the same factor. And then this is a smooth global Kranich chart of your modular space. So yeah, by the way, psi is the zero locus. This guy doesn't change the zero locus, so you have exactly the same zero locus. So this map will be still the original footprint map.
So the issue of like constructing this chart is kind of like, is it accurate to say that it's sort of orthogonal to the stuff that we were talking about?
First of all,
like, how do I say this? Is it correct to say that this is sort of like orthogonal to the thing we were talking about in the last lecture, in the sense that like if you had another construction of like this is just a particular construction of a global chart, right? But like if you had another way of doing this,
yes,
it would not like kind of the stuff you said last time. It doesn't require any special properties of this chart beyond just the stated properties of a global.
Well, yeah, it's certainly orthogonal to the last one. It's the last lecture is like, suppose we have.
Yes. So yeah, I guess I was just making sure that's the case.
So, right.
So this is just basically a very clever way of getting these global charts.
Yeah, it's
yeah, I think ultimately, so you have this compact modularized space. Of course, the nature is that you have things which can decompose and so on. So you just need a construction which, if you have the different parts, these things decompose, the parameter space also decomposes. So, that needs you, that gives you a lot of leverage if you have this many constructions.
Yeah.
Like in Floer theory, when you have this thing. You have a perturbation here, perturbation there, then it goes together, and if something you constructed decomposes the stuff you have. So it has to be something domain dependent on some level.
Yeah.
Yeah, so for example, one thing you need to do, for completeness is that you make a lot of choices in this construction, like for example this choice.
Yes.
You have to compare this choice.
As it's presented to you.
So, but typically, so for example, the smooth structure is not canonical, but there's a uniqueness part of Lashov's theorem. So you can always put two choices on two sides, and you build a trivial covariance, but you interpolate the structures.
So in this case, you have to stabilize again.
Stabilize again
so you have this structure here, then you stabilize again, and then it's connected.
You come out of this. Yes.
So are you going to use this like integrality of omega again for this sort of inductive construction of the whole of everything on the.
It needs this
So it's constructed
for.
Yeah, it's clear why you did it. It's clear why you need it here. Yeah, but then otherwise there's just no, I guess, bundle to talk about.
Right, you have to, yeah, if I want to use this method, then the bundle, you have how to describe the bundle. And there's a little, a few places where you use very, specific properties of the bundle and the curvature of the bundle. Yeah, so that's why in the case of Floer theory, we need this integrality condition to cook up those charts.